Let's do some exercises with our new Newton's second law knowledge. Exercise 1. Determine the accelerations that result when a 12 Newton net force is applied to a 3 kilogram object and then to a 6 kilogram object. So we really have two mini problems in here. Let's use Newton's second law to solve each of them. So we are using acceleration equals F net over m. Now the acceleration is 12 newtons, and first we are going to apply that 12 newtons to a 3 kilogram object. So using a little bit of mental math, we can see that the acceleration must be 4 meters per second squared. Let's do the second little mini problem. We still have that same 12 Newton force, and now we're going to apply it to a 6 kilogram object. So we'll put in 12 newtons as our net force, 6 kilograms is our mass, and yet again, we can do this in mental math. We find that the acceleration is 2 meters per second squared. And that makes sense, right? We doubled our denominator, so our answer got cut in half. That totally makes sense. So let's do another problem, but this one is a little bit more of a thinker. Suppose that a sled is accelerating at a rate of 2 meters per second squared. If the net force is tripled and the mass is doubled, what is the new acceleration of the sled? Now this one's a little bit hard because they don't give us very many numbers. We just know that acceleration is going to be 2 meters per second squared. And because of Newton's second law, we know that that must also be equal to F net over m. Now they don't do anything for us here except for tell us that we are now going to triple our net force, and we are going to double our mass, and we want to know what is the brand new acceleration. Now, if you want to, if you feel most comfortable doing this, this is what you should do. You should come up with some fake numbers for F net. You should come up with some fake numbers for M. Or sorry, I should say one fake number. So maybe your F net is 6, and maybe your mass is 3. Because if we do 6 divided by 3, that gives us our original acceleration of 2 meters per second squared. That'll help us solve the problem because if we now triple that net force, it's now 3 times 6, that's 18. And we double that mass, so that's 3 times 2, that is 6. Could you find out what this acceleration should be? Yeah. 18 divided by 6. Our new acceleration must be 3 meters per second squared. And that is a totally valid way to solve this problem. But I'm going to show you a second way to solve this problem. If you notice, we have a net force divided by mass right here. And we know that net force divided by mass must be equal to 2, because that's what we were told in the problem statement. So what we could do is we could say, all right, I got 3 over 2, but instead of writing F net over m, I'm going to write in that 2 meters per second squared. And by doing that, I get the exact same answer, 3 meters per second squared as the acceleration, which is awesome. That is what they are going to want you to do as you progress through school. If you decide to go through into a STEM field, you'll soon find that the numbers disappear and it's all letters. So this problem is a proportional reasoning problem. And you'll see these come up more and more throughout this class as we try to prepare you to see similar problems like this when you move on outside of high school. And in fact, there's a problem like this on your homework. It's problem number 3 on worksheet 1. You get a bunch of modified Atwood machines, just like how you had in your lab, and I don't give you any numbers to work with. But that's okay. You can still do it. Let's flip the page and do exercise 3. Exercise 3 is much more similar to what I'm going to be asking you guys to do on quizzes and tests. In the physics lab, Ernesto and Amanda apply a 34.5 Newton rightward force to a 4.52 kilogram cart to accelerate it across a horizontal surface at a rate of 1.28 meters per second squared. Determine the friction force acting on the cart. Now that was a lot of information given to us, so let's try to make some sense of that information by drawing a force diagram. Now this cart is sitting on a table, and that table is horizontal, so we know there must be a normal force and a friction force, and they must be equal to each other. Now we're told that we apply a force to the right, and it is a 34.5 Newton force. And there must be some kind of a friction force going to the left, and we don't know how big that friction force is, but we want to know. In order to solve this problem, we can use Newton's second law, and we're going to use it the way that we would have, in a way that looks very similar to what we did last unit. Because we're going to look at this force diagram, and from this force diagram, we are going to write a net force equation for those forces in the x direction. Now in the x direction, we have the applied force, and we have the force of friction. And so when we add that applied force and the force of friction together, that is going to give us our net force. And according to Newton's second law, net force is equal to ma. So now we can just fill in everything that we know. We know that the applied force is 34.5 newtons. We do not know the friction force, so we'll keep that as FF. The mass is 4.52 kilograms, and our acceleration is 1.28 meters per second squared. So once you do the algebra, this is really not so bad, and we find that the force of friction is equal to negative 28.72 newtons. And that negative sign is very important because don't forget, positives and negatives in this class refer to direction. And yes, that force of friction is in the opposite direction as the applied force. So if the applied force is positive, we want to make sure that our friction force is negative. We want to keep that on there. Let's do one last one. A block with mass 10 kilograms is placed on an inclined plane with angle 30 degrees. The force of friction on the block is 8.5 newtons. Draw a force diagram for the block. Find the magnitudes of all the forces. So there is a force of gravity acting on this block. There is a normal force acting perpendicular to the surface. And then there is a force of friction that is acting parallel to the surface. Now, if you guys remember what we did last unit when we saw things on a ramp, is we reimagined our x and our y-axis. So our new y-axis is going to be perpendicular to the ramp, and our new x-axis is going to be parallel to the ramp. That makes it so that we no longer have to break up quite as many forces into their components. The force of friction totally in the x direction, normal force totally in the y direction. We just need to break up that force of gravity into its components. So here's our nice little gravity right triangle. Now we want to find the magnitude of all of the forces. Well, the magnitude of the force of friction is given to us. It is 8.5 newtons, so ta-da, we are 1/3 of the way there. The force of gravity, now we know that is calculated by the formula 9.8 newtons per kilogram multiplied by mass. So we need to do 9.8 newtons per kilogram multiplied by 10 kilograms in order to get this force of gravity. This force of gravity must be equal to 98 newtons. And the force of friction, now we're going to really need to look at our force diagram right here. We know that the angle of the ramp is the same as this angle in our force of gravity triangle. And because this box is not jumping off of the ramp or being drilled into the ramp, the forces perpendicular to the ramp must be balanced. So therefore, the normal force must be the same as this long leg of our force of gravity right triangle. And if we wanted to calculate what that long leg is, we would use FG cosine of theta. So let's do it to find that normal force. Fn equals Fg cosine of theta. So we need to do 98 newtons times the cosine of 30 degrees. And when you put all of that into your calculator, you find that the normal force is 84.87 newtons. So ta-da! We have got the magnitudes of all the forces. Force of friction is 8.5 newtons, force of gravity is 98 newtons, normal force is 84.87 newtons. And this was not very exciting because we could have done this last unit. Let's do some Unit 5 stuff. Let's get some acceleration, some net force in here. And we're going to do that in Part B. Determine the acceleration of the block. So let's ask ourselves, what direction is this block going to accelerate? Well, it's probably going to accelerate down the ramp. If I know anything about blocks and ramps, blocks seem to always want to go down ramps. So what we're going to do first is we're going to write a net force equation, and we are going to sum all of the forces in the x direction for this ramp. So any forces that are parallel to the ramp. So parallel to the ramp, there is the force of friction, because that is pointed up the ramp. And then also parallel to the ramp is this parallel component of gravity. So we could calculate this parallel component of gravity using Fg sine of theta. And since this block is going to accelerate down the ramp, these must be unbalanced forces once we add them together. And so that must equal MA. Now let's plug in everything that we know. We know that FF, the magnitude is 8.5 newtons, but because it's pointed up the ramp, I'm going to say up the ramp is in the negative direction, so we're going to call that negative 8.5 newtons. Plus FG is 98 newtons. Our theta is 30 degrees, our mass is 10 kilograms, and we are looking for that mysterious A. So the physics is done. We are all algebra from here. And when you complete the algebra, you find that the acceleration must be 4.05 meters per second squared. And that's a positive 4.05. And we said that positive is down the ramp. So that seems pretty reasonable to me. 4.05 meters per second squared down the ramp. Fantastic.